This sixth exercise is about our set S omega. It has three parts. In part A, we have to prove that S omega has no largest element. In part B, we take any element alpha in S omega and consider this set. This is the set of those elements x in S omega that exceed alpha, that is, which are greater than alpha. You can think of it as the opposite of the section of S omega by alpha. We have to prove that every such subset is uncountable. And then in part C, we have this set. It's the set of those elements x in S omega which do not have immediate predecessors. We have to prove that this is also uncountable. So let's see the solution. Okay, so this is the solution. Part A is pretty easy. So we suppose that S omega has a largest element and let's call it A. Then the section SA of S omega by A is countable because that's what S omega is, that's how it behaves. All its sections are countable, but the set itself is uncountable. However, note that since A is the largest element, this section of S omega by A, that is SA, has almost everything in S omega except A itself, which means that if we take the union of SA and this singleton set A, we would get S omega back. But if this is countable, then this is also finite and hence countable. So the union would also be countable, that means S omega is countable. However, we know that S omega is uncountable. So this is the contradiction, which means that our supposition is wrong. So that is why S omega cannot have a largest element. Next, let's see B. Part B is also similar. We suppose that this set, the set of all elements x greater than alpha, is countable for some alpha, for some element alpha in S omega. Now the section of S omega by alpha, that is S alpha, is already known to be countable, and that is why countability of this set, and the singleton set alpha again gives us the fact that S omega is countable, which actually is not a fact. It is false because we know that S omega is uncountable, and that is why this supposition is wrong. That means for no alpha shall we have this set countable. It has to be uncountable. So it is just like part A. But the next part, part C, is somewhat different and it will be a little long. So let's see. We start the solution to part C by making up two notations. It will be helpful to us. For any element x in S omega, we denote by Px the immediate predecessor of x and by Sx the immediate successor of x. It's a different matter that these Px and Sx may not exist. When they exist, we will use these notations. That's why I have written if they exist. Okay, so with these notations, we now start. So what do we have to prove? We have to prove that x naught, the set of those elements in S omega which do not have immediate predecessors, is uncountable. Suppose it is countable. Okay. Then you recall the last result of this section, where we said that any countable subset of S omega has an upper bound in S omega, which is this theorem 10.3. So by that result, our x naught will also have an upper bound in S omega. And at the same time, x naught is a non-empty subset. Can you think of an element in S omega which will always be in x naught, which has no immediate predecessor? Yes. The smallest element of S omega is in x naught. How do we know that S omega has the smallest element? Because S omega is known to be well ordered. And what is the definition of a well ordered set? In it, every non-empty subset has a smallest element. In particular, S omega itself is a non-empty subset of itself. So it will also have a smallest element, which will of course be the smallest element of S omega. Why is S omega itself non-empty? Because it is uncountable. Obviously it will be non-empty. So that is why that smallest element at least is there in X naught. Now X naught becomes a non-empty subset of S omega which has an upper bound in S omega. So here we may be able to apply the least upper bound property provided S omega has that property, and that's the case because in exercise 1 it's actually very easy to prove why that is so. The content of this exercise is that any well ordered set has the least upper bound property. Okay, so by that property our X naught will also have a least upper bound or supremum. Let us call that Z, and that of course will be some element in S omega. Now where can we go from here? Let's see. The next question that arises is this: whether this least upper bound supremum of X naught belongs to X naught or does not belong to X naught. If it is not in X naught, what does that mean? X naught consists of those elements which do not have immediate predecessors. So not being in X naught means Z will have an immediate predecessor. That means Pz according to our notation exists. It's an element in S omega. Alright. And then what do I write? So there must exist an element U in X naught such that P of Z, Pz is less than U which is less than Z. Why? What is the reason for the existence of U and what is going on here? You see, Pz is the immediate predecessor of Z, which in particular means that Pz is less than Z. Okay. Because that's what happens with an immediate predecessor. Additionally, of course, there is no element between Z and Pz. That is also there. But the fact that Pz is less than Z makes Pz not an upper bound for X naught. Why? Because Z is the supremum of X naught. It is the least upper bound for X naught. So if I go even less than the least upper bound, so obviously that element, no such element will be an upper bound for X naught. So for this element to not be an upper bound for X naught, there should be at least one element in X naught which will exceed this element, because then only it will fail to be an upper bound. If everything of X naught lies on that side of Pz, then Pz becomes an upper bound. So that is why one such U will exist. And existence of U comes solely from the fact that this is the least upper bound for X naught. But then we have a problem, because by the definition of Pz, there should be nothing between Pz and Z. And that is why this condition cannot be true. So Z must be inside X naught. Okay, next. So next we consider this set, which may look very complicated at first. So let's go slowly, okay. The elements of this set B look like this. According to our notation, these are successors. This Sz is the successor of Z. Sz is the successor of Sz. This is the successor of this, and like that it goes. But that raises a question immediately. How do we know that these elements exist? They may not exist, no? Well, did you remember that at one point we proved, or in fact just observed, I should not maybe say prove because it's a very simple thing, that in any well-ordered set, except the last element, every element has an immediate successor. Okay, that just follows as an easy consequence of the definition of a well-ordered set. We are applying that fact here. Also recall that in part A, we have just proved that our S omega has no largest element. which means that no matter what element of S omega you choose, this Z after all is inside S omega. No, you will continue to get immediate successors. So for this one you get an immediate successor, for this one you will get another one, and if you are thinking of the order like this, in this direction it's increasing, then Z lies here, then this one, then this one, then this one. It's like the integers, for example. 1, then the immediate successor is 2, 3, and it goes on and on like that. Okay, so the set of such successive immediate successors is B, and it starts with the immediate successor of Z. Okay, so there is now no doubt about existence of B, and of course this notation quickly becomes unmanageable. So instead of these things, we have decided to call this one Z1, this one Z2, this one Z3, and so on. Now what we are going to claim about this set B is that B actually is nothing but the complement of SZ union Z. If we consider the section of S omega by that Z, that supremum of X naught, and take the union of that section with this singleton set Z, and then you remove that from S omega. So I mean, you can imagine a figure like this, just like the real line. You can think of S omega as a line, where at some location we have that Z. So whatever are less than Z that lie on that side. Okay, so that is this, and then the point Z of course is this. If you remove this part entirely, whatever you will be left with is this. There would be nothing else in S omega. That's what we are claiming. Now let us prove this claim, and this claim once proved will take us towards a contradiction, because you should not forget that we started our solution by supposing that X naught is countable, and we are hoping for a contradiction. So let us prove this claim now. In trying to prove that claim, that if you take the complement of SZ union Z in S omega, you will get B. The first thing we note is that B of course does not intersect SZ union Z. For our own benefit, I have drawn a figure here. You should understand that S omega actually cannot be represented like this. It's not the real number line, okay. But anyway, this figure at least shows how we can think of the order. So this entire line is in some sense representing S omega, a pictorial representation of the set S omega, where the understanding is that as you go leftward, elements decrease, you get smaller and smaller elements. Oh, and one more thing, yeah, I forgot. Because our set is well ordered, it will have a least element. Yeah, it won't go to the left indefinitely like that. Yeah. Okay, so S omega starts at some smallest element, and then the elements increase in this direction. Z is there somewhere, and the section of S omega by Z is this, SZ. And the successive successors that we get starting from Z, which are these. Okay. So the claim is that besides SZ, Z, and these elements in V, there is nothing else in S omega. At once it seems like this is natural, no, I mean it should be true. However, what is the guarantee that S omega has something on that far side which is not captured within B? There is one thing at least though, that there is nothing in between these things, because these are successive successors. But maybe there is something else on that side. Okay. But this disjointness at least is clear. There is nothing common to this part and this part. This part is our B and this part is of course this union. So our aim is to prove that if we remove SZ, Z and B from S omega, then we won't have anything left. Contrary to that, suppose there is something. So that something should be there on that side. Now think of that something. That something is of course this difference, state difference. If it is non-empty, after all it's a subset of S omega and S omega is well ordered, so that subset should have a smallest element. Let us call that smallest element C. And now, okay, next we have this. So what can we say about that element C? What is C? Let's first again recall what C is. C is the smallest element in the complement of SZ union singleton set Z union B. So in this diagram, where will C lie? Can C lie here? No, because if C lies here, then it's less than Z, so C will belong to SZ. That's not what C is. C is in the complement of the union of these three sets. C also cannot be equal to Z. C also does not belong to B. Now, is it possible for C to lie in between these successive successors? No, because they are successors. So there is nothing else in between them besides themselves. So we can understand that C has to lie, C has no other place to go other than lying on that far side of S omega. In particular, C will be greater than each Zn for all positive integers n. Alright. Now the immediate predecessor of C exists. Why? Because C lies on that side. C in particular cannot be an element of X naught because this is the least upper bound of X naught. So no element of X naught lies on the right side of Z. C however lies on the right side of Z. And what is X naught? X naught is the set of those elements in S omega which do not have immediate predecessors. But C is not there, so C will have an immediate predecessor, PC. Now where will this PC lie then? Well, note that PC is less than C. And what is C? C is the smallest element of the complement of the union of these three. Because PC is smaller than C, so PC itself cannot belong to that complement, which means that PC itself actually has to belong to the union of these three. But where in this union will PC lie? Well, obviously, these inequalities tell us that PC cannot be equal to Z. PC also is not less than Z, so PC cannot lie in SZ. So PC is forced to be an element of B because that's the only place left for PC to go. Okay, as such, these inequalities imply that PC belongs to B. But what is the set B? The set B has all successive successors and it doesn't end. It starts with the successor of Z and then it just goes on and on. So in particular, the successor of PC itself will also belong to B because that's how the structure of B is. It has all successors of all of its elements. However, the very definition of PC tells us that the immediate successor of PC is nothing but C. So C has to belong to B, but this is the contradiction because C lies in the complement of the union of these three sets. So something has gone wrong, and what went wrong is our supposition, which was, you remember what that last supposition is. We supposed that this is not the case, that besides B, this and this, there is something else in S omega. There can be nothing else in S omega. And that's why we have our claim established. Now let's see how we can use this claim to finally do it. Alright, so with our claim established, we now know that besides these three things, there is nothing else in S omega. The left hand side of Z, which is the section SZ, Z itself, and B. Now SZ is countable because every section of S omega is countable, and B is also countable. Because if you set up this map from the set of positive integers into B, which will map n onto Zn, then that's a bijection. Ideally, you should go through the little things that will tell you that this is the bijection, but it is so easy that I haven't shown it. You should, however, at least see it for yourself and be convinced that yes, it's really a bijection. So that makes S omega countable again, just like parts A and B, which is not true, and that is why our first supposition is wrong. Why first supposition? That is because we have run out of options. You may or may not have observed one thing about this solution. Part C. We started by supposing that x naught is countable, which is a lie. We want to prove that it is a lie. To hide this lie, we are going on telling lie after lie. But every time we do so and the situation becomes more complicated, we are getting caught and those avenues are closed. Okay, so you supposed something under that lie, you supposed something else. Now that was debunked as a lie. But now we have run out of options completely. We have to admit that we were lying from the very beginning. And that is why the first supposition is wrong. And that's why x naught is uncountable. Okay, so that's the proof. And let's just end the video here itself. Tomorrow we have something, of course, so we will see what it is. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.